Right, good morning. So today we will talk about construction of a transformer. The figure you see in front of you is that of a single lamination. Okay, so transformer, I will talk about it in detail, but first let me start from the basics. A transformer has a iron core. You would have seen. The iron core is made up of laminations. What you see in front of you is an example of lamination. Okay, lamination. So this is the lamination, and you have to bring multiple laminations to build the core of a transformer, which I will draw. So this is a lamination point. It is highly permeable. It is highly permeable, which means it provides an excellent path to magnetic field. So magnetic field can pass through highly permeable materials. Okay, so generally this in your books is mentioned as iron core, but generally it is silicon steel. Okay, silicon steel offers excellent permeability. Second thing is this lamination which you see in front of you is has high resistivity also. Resistivity. So the material has to have these two qualities, and it is very thin lamination. Okay, very thin lamination. So this is the way you build a transformer. You pick up one of these laminations, and it is highly permeable to ensure that there are minimum magnetic losses. It has high resistivity to take care of eddy currents. Eddy currents will become very low, and it is also very thin. And what you do is you also polish these with the help of a varnish. So these are polished. When you bring many such laminations together, okay, what you create is a core. Like talking about lamination, there is a type of lamination called as LL lamination. This is what actually is used in the construction of core transformers. So in class 12, what we study is core transformers. So one lamination I'm showing you has two pieces. They are joined together, and multiple laminations are used to create the core. What I showed you earlier was example of uh, a transformer core being constructed using a different type of lamination, but generally we use LL type of lamination to build transformers, which are in class 12. Thank you. All right, so what you see on the right hand side now is the iron core. Okay, so what you do is you bring many single laminations together, and these laminations, when you bring them together, these become an iron core. So this is the way iron core looks, but remember, each of the single lamination you take, okay, and the second one, for example, this is a lamination, this is another lamination. These are very thin, and they actually are very close to each other. They touch each other, but they are insulated from each other. Okay, they are insulated from each other. Insulated from each other. What you do is you polish them. There is a polish which is put on them. It's a coat like a paint, and so they cannot, when they touch each other, they don't short. Okay, they are insulated from each other. So what is the purpose of this core? This is the place where the magnetic field moves. Okay, so the use of core is that it provides magnetic path. Okay, it provides path to the magnetic field. Path to the magnetic field. I will show you the magnetic field flowing in the iron core. And just for your information, you can write iron core, and you can also use silicon steel. I told you silicon steel has very high permeability, so the magnetic losses are very low. This type of construction is used for class 12 purposes. So this is the core. It has a thickness. The purpose is that it provides path to the magnetic field. We will talk about from where does the magnetic field come and magnetic flux comes. Okay, so far what we have learned is a single lamination, and then what we have learned is bring many laminations together and create what is called as a core of the transformer. So let's move forward and study more things about the transformer. All right, so let's talk about the windings on the transformer. So what you see in the diagram 3, which is this, okay, the diagram 3, that this particular iron core or the silicon steel core now has winding on it. So the left hand side, what you see is called as the primary winding, okay, and the right hand side is called as the secondary winding. So the winding which you see here, okay, is called as the primary winding. So let me just label it for convenience. The winding is done on the core, okay, and this is your primary winding. What you see on the other side is called as the secondary winding. Okay. Secondary. So there are two windings which are done. Secondary winding. This is number one. And of course, you will connect an AC source alternating current. So remember, a transformer only works with alternating current voltage. So what you do is, as an input, you provided an input which is alternating voltage. The current is flowing, and the voltage which you provide is sinusoidal, right? If you've learned alternating currents, you know that the voltage you provide is sinusoidal in nature. So it's a sinusoidal. Okay, so the primary side is provided with a sinusoidal signal, and then there is a EMF which is generated in the primary winding, electromotive force. It's a back EMF because the flux is changing. Every current, so this is your current which is alternating current, produces a flux. And let me show you the flux which is traveling. Okay, so the flux looks like this. Let me show you an example. I told you that the core is used for moving the flux. So the flux is moving now, and the flux is moving here. Okay, so the flux is moving, and this is the flux. This is the flux. Okay, so the flux is now moving within the iron core. I told you it is used to create, allow, it's a highly permeable material, and it allows for movement of flux in it. So this is magnetic flux being referred to, and you can see the arms of the core, the two arms on which winding is done. Okay, and the other side, what happens is, which is the receiving side of it. So here you receive the voltage as an output voltage. So this is your output voltage. So this is your output, right? So this is also alternating in nature. So this is the way a transformer is constructed. You have these primary winding, which is nothing but a coil, a wire, and then you have the secondary winding. They are separated, but the actual coupling of these two, I am using the word coupling, just remember, is magnetic in nature, which means the same magnetic flux, it connects them. Okay, so this silicon steel core or the iron steel, is allowing this flux to pass through it. So this is your magnetic flux which is flowing through the core. Let's move to the next part of the transformer construction. All right, so let me draw the circuit diagram to help you understand more concepts of transformer. Okay, so let's say we are drawing the primary winding, and now this is on the core. We know the winding is on the core. So this is your primary winding, the primary winding, and I'm drawing this diagram so that in your examination you can see how you need to draw the diagram. So what you're providing on this side of the world is the primary side. So this is your source of voltage, right? So this is the source voltage being provided, and this winding has number of turns which are NP. The current which is entering is IP, P, right? When the changing current, because it's an alternating source, it's an AC source, enters the primary winding, which is here, it generates a flux which opposes this incoming current. Okay, so the flux which is generated is represented using this. This is your primary flux, okay, which is passing through the wire. So this is the primary flux. So this is phi primary, and the on the right hand side, what you have is another situation, and the number of turns don't have to be equal. They can be high or low. We will talk about it. Right now, we're just focusing on the circuit. And on the right hand side, what is happening is the flux, the which is generated by the primary side, which you see, there is a right hand to of it. So this right hand side of secondary, which I'm drawing now, has number of turns which are n secondary. So this was n primary on the left hand side, and now what we're drawing is the load side. Okay, so this side is called as source, this side is called load. Load is like your fan, your refrigerator, and stuff like that. So the load is connected here, and now what is happening is these two are now having a magnetic flux which is between these two, okay, between these two, and this flux is called as the mutual flux. Mutual flux. So this is the flux which we saw in our earlier diagram, which was flowing through the transformer core. So if I have to draw the transformer here, this part is the transformer, which is the two limbs or the arms of the transformer. So if I were to show you those limbs, and tell you where these are, so I'm referring to this winding, okay, this particular winding, the primary winding and the secondary winding. This is what I've drawn. I have not drawn the core, of course, but the flux which I'm drawing as the mutual flux is this one. Okay, this is the mutual flux which I have drawn in the diagram. So, but I'm not using the core, obviously. What I'm doing is just drawing the circuit. Okay, so the part which is showing you the mutual flux, okay, the mutual flux phi m is this. So this part is the transformer. Okay, from here to here, it is called as transformer, right? So this side is this is the primary flux. Primary flux is this. This is the primary flux, and on the right hand side, what you see is the mutual flux. I hope this is clear to you. This is the way you need to draw the diagrams. Okay. Now let's talk about why all this is being done. Okay. And you can see what is happening. I will just elaborate on the way it works on this diagram. So this is what you do. What you're doing is you are supplying electrical energy to this device called as transformer. So the electrical energy is coming through the alternating current source. That electrical energy is getting converted into the magnetic energy, which is this, right? The magnetic flux. So this is the area. The core is the place where the electrical energy is getting converted into the magnetic energy, and then this magnetic energy converts back to electrical energy on the right hand side of the load. Okay, the output side is called as the load side. So if you see if I have to draw a high level diagram, the way I would like to show the transformer is that you have a device, and I'm not drawing, I'm just drawing a high level diagram. Okay, and so that you can memorize or easily understand. Okay, so what you're doing is you're providing electrical energy which gets converted into magnetic energy, magnetic field energy, you can say, right? The flux part of it. And then on the right hand side, what is happening is the electrical energy. So the first part is electrical energy, then magnetic energy in the form of the field, and the other side is again electrical energy. So you can see the electrical energy is getting converted to magnetic field, and then the magnetic field is converting back to the electrical energy. So you would have heard that the when the power is transmitted from the power stations or in your neighborhood, transformers are available to scale up the voltage or scale down the voltage. But note, a transformer is nothing but a device which is converting electrical energy to magnetic and then magnetic to electrical energy. What it does on its own is something what we will study now. Why this conversion is happening, what is the role of windings, and what is the use of transformer is our next lecture. Thank you. So I talked about coupling. Coupling is very important for a transformer, and I have shown you 5P, which is the magnetic flux in the primary. Then I have shown you the transformer magnetic flux, which is phi mutual. And then there is another flux, which is phi secondary. Obviously, you have a secondary wire. So you will have a third type of flux in it, which is this. Okay. So the flux in the secondary winding is also there. Okay. We must know that there are three types of fluxes which are moving in the transformer. Now, when it comes to coupling, you must understand and memorize this part, that if the in an ideal transformer which has no losses, okay, the magnetic field is not leak, there is no leak in the magnetic field flux, the phi primary is equal to flux in which is mutual flux is equal to flux which is secondary, right? So there are three types of fluxes which are there, and if they all are equal, then we say that the coupling is ideal and the value of coupling is 1. So this is a maximum coupling of a transformer. Okay. Otherwise, when there is a loss of flux, which means not complete flux, which starts from the primary side, is able to reach the secondary side, losses are there, then the value of coupling is always less than 1. So coefficient of coupling is this situation when the flux in all the windings is same, and even the mutual flux that connects the two cores or the two sides of the transformer is also equal to primary and secondary. So the concept of coupling is very important and decides the efficiency, and therefore a good mention or a brief mention was required. Now there is a the instantaneous voltage in the coils of the transformer. Okay, so the instantaneous voltage, for example, on the primary side is given by EP, the instantaneous voltage available on the secondary side, so I'm referring to instantaneous voltages. Okay, and the number of primary turns is NP, and the number of turns on the secondary side is NS. Okay, now we are not going to get into derivation of how these instantaneous voltages and number of turns are linked, but this is the way it is linked. So instantaneous voltage across primary divided by instantaneous voltage across secondary is equal to NP divided by NS. This is the final thing you have to know. And if you are supplying an input voltage, which I showed you in the diagram, okay, if you remember, I showed you a diagram. This is the input voltage, right? So this side is this input voltage, if you know this, and you know the output voltage. So what I've written as the instantaneous value, EP upon ES, is equal to NP by NS. Okay, this is equal to the input voltage divided by the output voltage which is available to the load. Okay, this ratio, right, this ratio is applicable for the situations when there is coefficient of coupling is 1, which means there is no loss of the flux. You must remember this, that you can't apply this if phi S, phi P is equal to phi mutual is equal to phi S. Only then this is applicable, because we study this is a case of ideal transformer, ideal transformer. transformer. Okay, so an ideal transformer is what we are studying, and remember these rules which I've just written. So this is the input voltage, this is the output voltage. Okay, the and for example, you're given the value of input voltage as 314 sine omega t, right? This is your input voltage, and this is being referred to the max. Okay, and the output voltage is given by V output is, for example, 200 sine omega t, right? So you can divide these two. This is what is being referred to. Okay, and this is instantaneous. You can also write the maximum voltages here, as a ratio, which is this, because finally sine omega t gets cancelled. I hope this is clear that this ratio, we are not doing derivation of this particular formula, but we must understand this ratio, because this is what will decide how the transformer is to be used. I hope this is making sense to you. All right, so let's study these ratios. Now this ratio is called as the transformation ratio. Okay, so I am using a new terminology called as transformation ratio. Okay, and transformation ratio, what it means is, for example, if you can see, the voltages have been linked with the turns. So this is the number of turns. So if I write V input, which is on the input side, I am referring to this as VG. You can write V input also. V input divided by V output. Output is the secondary, the load side is equal to the primary turns, and because input is always, so I will write as N secondary, right? So you can see the output and input voltage ratio is dependent on the turns. Now turns are something you can control, right? During the construction, you can decide how many turns you will have here and how many turns will you have here. It is your choice. If you find that the number of turns in the primary side is greater than the number of secondary side, which means that V input is greater than V output, or V output, which is the secondary side, is less than the primary side voltage, after the complete transformation happens. Transformation means what? The conversion of electrical energy to magnetic field, and then magnetic field into electrical energy. So energy is getting transformed, changing. So it is very much dependent on the ratio of the turns. This is very important. The ratio is called as transformation ratio, where the output voltage is less than the input voltage because of NP being greater than NS. Such a transformer is called as a step down transformer. Step down. So if you keep the primary side turns, the number of turns on the secondary side is less, so you can see the greater than sign. The voltage you receive on this side, right, which I'm referring to V output, becomes low as compared to this voltage, right, which is a primary voltage. Such transformers are used to reduce the voltage of the input signal. And in your houses, when you get the uh, electricity, the voltage that comes from power station or from the nearby electricity office is very high, and you have to bring it down. So all the transformers that you see near your house are doing a job of reducing the voltage. That is, the correct word is step down. Okay, so step down. Now let's talk about the uh, reverse situation, when you find that the output voltage has become greater than the input voltage. So I will just use the same formula of NP by NS. But this time what you're finding is that the output you're getting is greater than the input voltage. Input is on the primary, output is secondary. If you think about this, then NS, right? In this situation, NS is greater than NP. Now, this situation, NS is greater than NP, is the situation of the where the voltage has increased. Okay, so the voltage has been amplified. So the transformation is on the higher side. Such a transformer is called as step up transformer. Okay, step up. So it increases the voltage on the right hand side, the load side of things. So this is very important, the concept of transformation ratio, and how there are two types of transformers available to you. The step down transformer, where the voltage is lower on the secondary side, and a step up transformer, where the voltage is higher on the secondary side. And what is happening is the control mechanism is the turns. Okay, the number of turns, the ratio is deciding whether the transformer will become a step up transformer or a step down transformer. So turns are very important for a transformer. This is the controlling mechanism to decide what type of transformer will you finally get. So memorize this as a shortcut. If you find the transformation ratio A, we generally use A is less than 1. It's a step up transformer. If the transformation ratio is greater than 1, it's a step down transformer, right? So the transformation ratio is what? NP by NS is the transformation ratio. So memorize this. It will be very useful when you solve the numericals. So the final word on the transformer is this. Okay, so now we know there is a input current also. So another equation that you must understand apart from transformation ratio is that the V input, which is a primary side, divided by V output, is equal to the N primary divided by NS is equal to, this is what is important to understand, I secondary upon I primary. Okay, so this is the transformation ratio. It can be expressed in voltages, it can be expressed in number of turns, it can also be expressed by way of the current in secondary and primary. In an ideal transformation, whatever power that comes from the input side, because there is no loss, there is coefficient of coupling is 1, no flux gets lost, there are no losses, it's a perfect transformer. So the power which you get on the other side of the secondary is the same as the input. So these two equations, the ratio, this is the ratio equation of transformation ratio, which we have already studied, and the power. Please ensure that when you start doing numericals, these are the two which will be most handy to start with. So this video was basic video to make you understand what is a transformation, etc., and how ratios are impacting whether the transformer is step up, step down, and this was for an ideal transformer. As we progress in my next video, I will go deep inside the transformer to discuss some more important elements. So for today, it is, I think, enough. Try and digest this information. This channel has 127 videos on alternating current. No one will explain you the level of detail available in this channel. So if you subscribe to this channel, you can sit at the comfort of your home and watch the complete physics course free of cost. Thank you.